So let's look at our methyl trityl ether experiment. Our starting material was triphenylmethanol. We already assigned that last discussion. We'll move on to this one. We don't have nice peak picking done on this because it comes right off of NIST. But we'll try and speed this up because you guys are definitely getting better at this. The ether stretch, the CO stretch, you'll see clear as day in this one. You should see a relatively strong peak right around 1080. These two right here, 757-ish, 705, those are your mono-substituted aromatic ring out of plane bend. These right here, see that one right there? That one's right around 1600-ish in these two. So this collection here in this spectrum is actually your carbon-carbon double bond of the aromatic ring stretch. And then over here, these peaks that are just that side of the 3000 line. If you want, you can get your protractor and a ruler and draw the 3000 line. Anything that side of it would be your sp3 hybridized carbon with a hydrogen stretch, which is right there, right? sp3 hybridized carbon and hydrogens on it stretching. The rest of this stuff here is the sp2 carbons on the phenyl rings with the hydrogen stretching. So that pretty much handles our IRs. If we move on, and we already looked at this one, the C13 of your starting material for this one. Now what I've done this time around is I've double checked a few things when I was marking. This is one of the ways I labeled it. I've done it in class where you see your two ortho carbons. And I've just forgot one, haven't I? If I went A, B, C, D, then obviously I'd have to label this one as E. And I'd have to go over here and I'd label this one as F. So we're good. Okay. So we expect to see the attachment carbon that I've labeled E. It's usually a quaternary one and very short. So you go to your aromatic region and obviously it would be the short one. Notice we talked about this last time. This one here is very, very tall. And it actually turns out that the C carbon, right, is very, very likely to be that one. And then the A and the B happen to overlap and create this very big one here. All that's left over now is this sp3 carbon we've labeled D, and we made a note of it right here online. These first three is from chloroform, but this one will be D, and I made a note of it right there. Let's look at the proton. It turns out that all of the aromatic hydrogens happen to give almost a perfect singlet. So when I ran the stuff right out of the bottle, clear as day, you see essentially almost a perfect singlet. Then you go over here, sometimes you see it, sometimes you don't, but that's the hydrogen itself on the oxygen. So that's your starting material. You've already done that last week. Let's look at our product. This was a pretty good product, very, very pure, that a student had run. This was Zuber and Ken, and that'd be 2012. Look at that nice aromatic monosubstitute, the classic. This is going to be your quaternary attachment point of the benzene ring. This will be the one in sort of the ortho position. There's only one of them. And then these two, almost the same height, will be A and B. So the attachment carbon F, we already labeled. C was the second highest, and A and B are the other two tall ones. D, we're going to find that very similarly. You can just start to make out the three peaks of your chloroform D. This one has to be carbon D, and the classic one near 50 is the carbon of a methoxy group. That would be E. So that one came out very nice for Ken and Zuber. When I got a proton, Caitlin and Ashley, their proton of theirs came out reasonably pure. And the only reason why I know that is you don't see that characteristic giant singlet of the starting material. You don't see really any benzophenone left over. So this right here is pretty nice. This is exactly what you would expect. And again, can we definitively label the two humps? Not really. We can just circle this and say it's all of your aromatic hydrogens. And then, of course, the singlet for the O-methyl. We've learned about this in spectroscopy. We know that the hydrogens on a methoxy carbon, okay, they're somewhere usually between 3 and 3.5. Now this one here came out to 2.99. I think on the wall I said it's 3.07 or something. You basically called it dead on 3 pretty much. Now this individual had essentially nothing else except, see that little triplet? That's a trace of ether perhaps. But in any event, that's their methoxy peak. So that's a pretty nice looking pure, reasonably pure product NMR. That's what it would look like. Now let's look at another student. Same year, this is Taryn and Ashley's. You can clearly see the one that's right almost at 3 parts per million, integrated to 3. That singlet is the methoxy of their product. The bigger singlet next to it at 3 point, a number on that, 3.5-ish, that's methanol. So a lot of people have leftover methanol. And you can see here, there's 1, 2 buried in that's the quartet of diethyl ether and the triplet of diethyl ether. And that was TMS. So they had a little bit of diethyl ether left in theirs. You can even see a hump here, which could be the OH of their starting material. How do I know they have starting material? Look at this. You can see a little bit of leftover benzophenone, right? Remember the student above? Totally flat in here. The broad forest structure is the product, but that pervasive giant singlet is leftover starting material. So this is very common to see happening. You may even see a few extra peaks, but it's very common. And the idea there would be to try and integrate, like this one, we have integrals from the ratio of methanol to their product. So we could at least correct their yield for methanol, for instance. The diethyl ether, yeah, there is an integral there. You could correct for that too. But that's the gist of it.